Hey everybody, I'm Michael,
I'm Ryan.
And I'm Colton.
and today we'll be teaching you guys a little bit about turbo machines. Okay, so a turbo machine is a mechanical device that consists of several blades attached to a rotor, and they're used in industry to either extract energy from a fluid or add energy to a fluid. And turbo machines can use either liquids or gases as their fluid, and the use depends on the situation that the turbo machine is in and the type of turbo machine.
There are many common uses and applications of turbo machines. Pumps and compressors are found everywhere in the chemical industry, oil refineries, food processing, paper mills, and more. Fans, both industrial and like residential fans, are a type of turbo machine. Windmills are commonly used as a turbo machine. Also, hydroelectric turbines and dams, and car engines, jet engines, rocket engines, any type of vehicle can use turbo machines.
Now moving on to the classifications of turbo machines. There are three main classifications, which are determined by the predominant direction of the fluid motion relative to the rotor axis. The first classification being axial flow, in which the fluid maintains its axis from the inlet to the outlet of the rotor. The second being radial flow, in which the flow across the blades pertain to the rotor inlet, exit, or both. And lastly, mixed flow is combining components of both axial and radial flow.
So let's talk about the basic physics of a turbo machine. So let's consider a simple turbo machine that rotates at the set angular velocity of omega, and its blades all have a velocity of u, which is denoted as omega, the radial velocity, times their radial length. So we have a fluid flowing towards the turbo machine with a velocity of v1, and we have a fluid that flows outwards from the turbo machine with a velocity of v2. So for a simple pump, V1 flows towards the pump with no tangential component in the completely axial direction. And as it goes through the pump, the blades on the pump transfer kinetic energy to the fluid. And as it exits the pump, the fluid now has a new tangential component of velocity that is tangential to the rotation of the blades, as we can see in the diagram on the right. For a turbine, it is very similar. V1 initially has no tangential component. It is axial velocity. As it moves towards the pump, it comes in contact with the blades. But unlike the pump, which pushes the fluid in the same direction of its blades, the fluid pushes the blades in the opposite direction of its new velocity. Through the conservation of momentum, as the blades get pushed down, the fluid gets pushed up, once again with a new tangential component of velocity in V2. Let's consider a little bit about the angular momentum of this fluid. So we can sum up all the external torques of the shaft on the fluid on the left-hand side of the top equation. And then the right-hand side of the equation is essentially the sum of all the angular momentum before and after the fluid moves to the turbo machine, as denoted by that integral. And then through a one-dimensional simplification, we get the torque equation seen below. We also have two other important equations. One is the power equation for the shaft. This is equal to the torque done by the shaft times the angular velocity of said shaft. And that is the result of that multiplication as seen on the right. And for the work per unit mass done by the shaft, we take the power of the shaft and divide it by the mass flow rate of the fluid. And once again, we get the equation seen on the right.
Now moving on to pumps. So the first pump I want to talk about is a centrifugal pump, which is a common radial flow turbo machine. So it has two main components: an impeller, which is attached to a rotating shaft, and a stationary housing, which encloses the impeller. The figure shown is known as a diffuser pipe, in which the fluid discharges directly into a volute-shaped casing. The casing then produces a uniform velocity distribution, and the diffuser vanes at the end then decelerate the flow as it is directed towards the casing. And this is all shown in the figure to the right. So with a centrifugal pump, there are two main governing equations, one being for the shaft torque, which is the density times the flow rate, times the difference in two different radial components and velocity components. And the other is the shaft work created by the pump, in which it is also the velocity. It is the difference in shaft work times the flow rate and density. And now moving on to axial and mixed flow pumps. So axial flow pumps consist of a propeller confused within a cylindrical casing, often called propeller pumps. This is used when high flow rates at low heads are required, which is difficult for centrifugal pumps. For example, in the figure shown, the flow is in the axial direction as opposed to the radial direction, which is seen with centrifugal pumps. And how this works is the rotor is connected to a motor through a shaft, and as the blades rotate at a high speed, the fluid is sucked through the pipe against gravity. And mixed flow pumps, again, both combine characteristics from centrifugal and axial flow pumps together.
Okay, let's talk a little bit about turbines now. So a turbine is a turbo machine that extracts energy from a fluid, and it does this by exerting a torque on a shaft, which spins, generates mechanical energy, and then a generator will convert this mechanical energy through electrical energy. And you can see this in the diagram to the right. And today we will mostly be focusing on hydraulic turbines because water doesn't have a density drop across the blades like a gas might. When the temperature and pressure are changing, the density can also change. And there are two main categories that turbines are broken into, which are impulse and reaction turbines, and they are distinguished by their mechanisms. First, let's talk about impulse turbines. You can see a picture of one on the right. And in an impulse turbine, the only force that acts on the blades is the force due to the velocity of the fluid. There is no appreciable pressure drop across the blades, only a pressure drop across the nozzle. And there are two main types of impulse turbines that are commonly used in industry, which are the Pelton wheel and the dental drill. So first, the Pelton wheel is typically used in a situation where there's a high head and a low flow rate. And a good example of this is a dam. So like, as you can see in the figure to the right, you have a dam and a pipe that leads down from the dam to the turbine, and it gains potential energy to the nozzle, which shoots the water at the blades of the turbine. And here the power is affected by several different conditions, which are the shape of the buckets, the angle of which the exit edge of the blade is, which is denoted as beta, the mass flow rate, and the velocity of the fluid stream. And we have some important equations down here, which is the work of the shaft and the torque of the shaft, which depend on the mass flow rate, the velocity, and the angle beta. And then we also have an equation that shows that maximum power happens when at the condition V1/2. And here we have a dental drill pictured at the right. And this is the type of drill that a dentist would use to fill a cavity or whatnot. And in this case, air is used in place of water, and it utilizes axial flow. And this case is special because to change the absolute velocity, the blades must push the fluid in the opposite direction of the motion of the blades. And then the second main type of turbine are reaction turbines. And in this case, they are typically used in lower head and high velocity scenarios. And unlike impulse turbines, there is a pressure drop across both the nozzle and the blades. And unlike the impulse turbine, the only force isn't due to the fluid motion. There's also a force due to fluid pressure across the blades. And there's a picture of reaction turbines on the right. And we have a couple of equations, the first of which is the efficiency, which depends on the work of the shaft, the density of the fluid, gravity, the flow rate, and the height. And then we also have specific speed, which is a non-dimensional quantity that depends on the angular velocity, the work of the shaft, and height. And yeah, these are our references. I hope you guys learned something in this presentation, and have a good day.